This is my 5th physics lab report. So there's a bunch of formula here to get through, so I'm going to try to make this intro slide quick. So a quick little summary slash purpose of this lab was to model the time of a magnet falling through an aluminum foil tube for both in real life and also computationally. And computationally, we also plot a velocity versus time graph. Now, some of the formula involved in this, it's mainly Faraday's law, but to build up to that, we need to know the magnetic field of a dipole general equation, which is right here. And then we need to know Faraday's law, which basically states that an increasing flux, which is the amount of magnetic field going through an area, the change in flux is actually related to a change in a non-Coulombic electric field, which drives a current, which actually formulaically is just the time derivative of flux is equal to the magnitude of your EMF, which is your generated volts. So you use that, and then you use V equals IR, and you can solve for your induced current based on your resistance and your induced EMF. Now, we also need to know the force of a magnetic dipole on a ring, which is over here, and we need to know Newton's second law, stating that the force of a magnet on a ring is equal to the force of the ring on the magnet. And a brief little preview up here is our velocity versus time graph right up here. Now, our experimental setup here was basically just dropping a magnet down an aluminum foil tube. So what I did was I just held the tube and magnet in one hand, let go of the magnet by moving two of my fingers, and then just recorded it with my other hand holding my phone. So that was that. Some physics errors that could be present were the angle of the tube. Maybe I was angling it a little bit. The magnet was rotating, definitely moving a lot in the tube. So maybe, it moving around screwed up the magnetic field and had some weird errors there. The system is the magnet in the tube, the surroundings is everything else, and the initial conditions is the magnet resting right above the tube right before I drop it. So coding, let's get through this quickly because there's a lot to go through. There's over 200 lines. So up here's my physical constants. Over here, this is plot setup. Over here, this is tube setup, just iterating through and creating rings and also, width, length, yada yada. Over here, we start with magnet setup, which continues on over to here. Here's more magnet setup. We also input the magnetic dipole calculated from a previous lab, because it's the same magnet. Here's some initial conditions. Here is calculating the magnetic field at a current observation location, just general equation for a dipole. This is called later. This calculates the change in flux over time, which is your induced EMF, and this is called upon later. And over here is where we start doing simulation stuff, just basically iterating through time. So as you can see here, it just waits a little bit and then goes through and calculates, as we can see over here, the force induced. And to get to the force, of course, you have to calculate your change. You have to calculate your magnetic field at the ring, and then you calculate how that's changing by getting your, change in EMF or change in magnetic flux over time. And then you use that to find your current using resistivity and, your EMF, which is your volts, right? So you find your current, and then using the formula discussed in the lecture video we were told to watch, and it was also shown earlier, we are able to calculate the force of the magnet on a ring, and then just flip that around using Newton's second law, and we can find the force of a ring on a magnet, and then we just did that for all the rings. So that's how you sum up the magnetic force. And then over here, what we do is we actually add the gravitational force to the magnetic field, or not magnetic field, the magnetic force. And then we just use this down here. This is just purely kinematics. We get a net acceleration by dividing out the mass of that force. And then, yeah, we just step through the velocity and step through the position, and we just show those. And then down here, it's just more plotting stuff. So the computational model modeled that the magnet fell through the tube in about 0.87 seconds, and in real time was about 0.98 seconds. So what I'm thinking could be the biggest source of error here is there not being enough rings in the computational model, so there's not enough force, contributing to the magnet slowing down. Also, maybe some measurements were off, like mass or, dimensions of the tube. Either of those probably were the big ones, I'd imagine. So some quick conclusion questions. What if the resistivity of the conductor were changed to be as close as possible to zero? Well, lower resistivity would lead to a higher current, thanks to V equals IR, and a higher current would lead to a higher force, so the magnet would fall slower, take longer to get through the tube. What if holes or slots were cut into the tube? I would argue that cutting a hole or slot would increase the length of each little loop because it has to go around the hole. And due to the way resistivity works, that would have a higher resistance, meaning a lower current, so lower force. Now, red, I argued, is counterclockwise current because as a magnet falls down, its flux is increasing going down. So that means thanks to Faraday's law, the induced magnetic field has to be the other way to counteract that. So it's going up. So if you point your thumb up, curl around, counterclockwise, boom. And the red rings are down below. So like I said, magnetic field flux increasing going down. Point your thumb up, curl around, counterclockwise. What happens to the dynamics of the system you flip the magnet around? Absolutely nothing. Still takes the same amount of time to fall down. How does the total time in the real world compare to that of my computational system? It took a little more time in the real world. We discussed that earlier. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? I argue that they counteract each other. They get to an equilibrium position, it gets to a constant velocity, so the net force is 0, meaning that the magnetic force gets up to the gravitational force.